Okay, today we're going to look at some applications of the Langmuir isotherm. And the first thing we're going to do is just recast the isotherm in terms of concentrations rather than pressures, like we did in the previous video. And here we can think about all sorts of different binding situations, like a drug receptor, neurotransmitter, ion channel, something like that. And so our model here is going to be a ligand plus receptor in equilibrium with the ligand receptor. It's bonded together. All right. So we can write the equilibrium constant for this. And we can solve for, we re-express this for LR. And then we can ask, what is the fraction of bound receptors? So, fraction of bound receptors. And then we can replace the LR with our expression from K. And the great thing that buys us is that we can cancel out the receptor concentration, which is a hard thing to measure, and cast this in terms of the equilibrium constant and the ligand concentration, which is usually a little bit easier to measure. All right, and so this is the Langmuir isotherm. For the scenario of a ligand and a receptor, so neurotransmitter, ion channel, drug, receptor, protein, and so on. And again, we'll just remind us of the graph. Y is a fraction of open channel, so it's between 0 and 1. And asymptotically, we go to 1. Ligand concentration, when that is 0, we're 0. And we get the familiar saturation curve of the Langmuir isotherm. And then we look at this special point. And this is the ligand concentration that gives us 1/2. And this is equal to 1/K. So if we can find the half fraction ligand concentration, we can find that from the value of K. Or we can find K from that value. All right, so that's our first application. Let's now do a second application in which we develop the enthalpy of adsorption and an analog to the Clausius-Clapeyron equation. So application 2 here. So let's draw our picture again. This is a picture we had in the first video on the Langmuir isotherm. And we get some equilibrium binding between that. And our question is, if this is a gas particle with pressure P, and here's a binding site S, G plus S goes to GS, what is the expression for delta H of adsorption? Okay, well, this is equilibrium. So at equilibrium, the chemical potentials are equal. So we can express the chemical potential for the gas and the chemical potential for this GS. I'm going to write that as A for the adsorbed compound. Now, in general, if this is equal, it doesn't necessarily mean that this is going to be true. But we are free to choose the path of a little differential. And because we're always working with state functions here, then any result we get will be valid regardless of path. So we're going to choose a particular disturbance from here such that this is also true. Okay? So this is key here because du is minus S m dt. This is the molar entropy plus V molar dp. Okay, so that's true for any chemical potential there, and when expressed in terms of when the natural variables are T and P. So we have this expression becomes minus S G molar plus V G molar dt. dt plus V G molar dp equals minus S A molar dt plus V A molar dp. Okay. Now I'm going to get my S's over to one side. So I'm going to have SA molar minus SG molar dt, and get my V's over to the other side. It's going to be VA molar minus VG molar dp. Let's see, is that right? Yep. Okay, now this is, as expressed this way, this is final minus initial. So this is delta S. I should write this delta S molar. That's the molar change in entropy for the adsorption. dt equals. Now here, this is approximately Vg molar, because this is the molar volume of the gas compared to the molar volume of particles adsorbed to the surface. And so the gas takes up a much larger volume to the extent that, for all intents and purposes, at least at room pressures, or at modest pressures, this is just V gas. And so it's negative, it should be negative V gas. So minus V gas molar dp. Okay. So now, for an ideal gas, V G molar is RT over P. So we can put this in, and we get delta S adsorption dt equals minus RT over P dP. Now I could express this, let me just clear out and get just ds, so I'll bring this, or just delta S, so I'll bring this dt over here. So I get delta adsorption S equals minus RT over P dP. And this is molar, I should always remember that's the molar quantity. So we multiply by n, number of moles on each side for the quantity for an arbitrary amount. All right, so we've got this. So this is the molar entropy change, so that's something good to get. Let's get all the way to the delta H. So we know for any reaction, this is the case. So certainly true for this one. So we have delta G adsorption molar equals delta H adsorption molar minus T delta adsorption S. Now at equilibrium, this is equal to 0. And so we have that. Now we're very close. We'll just stick this into here. It's a t squared because we have a t here and this extra t right here. This is the Clapeyron equation for adsorption. So this would be the analog of a vapor to liquid Clausius-Clapeyron equation. So to answer our original question, then we would just multiply by n. So let's bring us back to our original question. What is this? And we just have n there. And just want to make one more note before we go on to the next application. This is the logarithmic derivative here. So we notice this 1 over p out front. So you'll sometimes see this like this. And I think I missed a minus sign. Yeah, minus sign here. So we'll sometimes see that. And so if you were to plot LNP versus T. We have a negative slope. So the slope of this line would be over nRT. So sometimes you'll see it this way because it linearizes that if we were to plot versus the log of the pressure. All right, let's look at one more modern example, that of gas delivery. So here, let's imagine a piston under high pressure, and we're going to compare, well, not compare, I would say we'll have a mechanism for going back and forth to low pressure. And we can see that the equilibrium will shift to more adsorption, less adsorption. And so the question will be, how much gas can we store here, and then how much is released when we go to lower pressure? So how much can be stored under high pressure on the surface, and then how much is released when we go to when we release that pressure? All right, so the number released is called N del. This is the number of deliverable gas particles. And N del. So N del then is going to be sigma naught. So this is sigma naught is the number of surface sites, and times the fraction of surface sites that are released then when we go to a lower pressure. We call that Y del. Now Y del is just going to be the Y under the high pressure conditions minus the Y under the low pressure conditions. And the operating assumption here is that the binding constant doesn't change with pressure, and that's usually a pretty good approximation. Okay, so let's sketch a little picture here. Here's Y, here's our pressure, and again, if this is our just normal Y, so our normal Langmuir isotherm, then we have the pressure low and the pressure, some pressure high. that will be the y del there. Okay, so the important question is what is the optimal k for this? So let's see if we can figure that out. Well, if it's an optimal, if we're looking for an optimal k, then it's a calculus problem, and we take the derivative, set it equal to 0, and find a optimum, find a maximum y del. And the reason this is important is because if you have too strong of binding, right, then you don't get enough release. If you don't get enough binding, then you don't get enough packing, storing, and so there needs to be some compromise between too much good binding, but also being able to release that number. And so there is an optimal k, so let's try to find that. So we consider the derivative of y del with respect to k. So this is going to get squared down here. We're going to leave the pH up top. And then we set this equal to 0. Let's go ahead and do that. And we solve for k. Now that takes a bit of algebra, so I just use Mathematica to solve it. And when we do that, y del is a max when one solution, the physically relevant solution here, is when k is equal to 1 over the square root of pH PL. And we'll call this the k optimal. All right, so that's a good solution. We can check here. Units are right because it should be 1 over pressure, and we've got pressure squared, square root of that, so we have 1 over pressure. Units work out okay. Let's go back to y del, and let's put in k optimal. So we'll call this, what is y del under optimal conditions, optimal k? Well, let's plug that in. So this is going to leave a square root of pH over PL. And this will be the reverse. This will be PL over pH. And let's help ourselves out here. Let's let x equal that. So then we have that. We can simplify this. And so starting to simplify a bit, but now let's put this back in. and I can multiply through by square root of PL, so I get square root of PH minus square root of PL. So I'll do that on top and bottom, equals square root of PH plus square root of PL. It's our value when we have the optimal K. So let's put in some typical numbers for some industrial practice. So let's let pH equals 6.5 megapascal and PL equals 0.5 megapascal. All right, and so let's get the fraction of, or let's get the Weidel optimal. And we can work that out, and I think that comes out to be 0.57. So when we're looking on the graph, we're getting a range here. And given this curve, that's not the shape of that curve. That's not too bad. So 57% there. All right. So these are a few applications of just a simple Langmuir model, and so we can see that this just touched the surface of where the Langmuir model is used, and we see direct application in drug binding, neuroscience, neurochemistry with neurotransmitters binding to ion channels. We got in some thermodynamics when we looked at the delta H and the Clausius-Clapeyron version for equation for adsorption. And then here we look at a little bit of a industrial application where we're using pressure differences from one state to another to deliver gases. So we use high pressure to adsorb a bunch of gas to the surface, and then lower pressure to release that gas.